metric space to another metric space, which is an isometry. What does it mean that it's an isometry? Yes, it means that the distance is preserved. It means that here, the distance between f of x and f of y is equal to the distance between x and y for every x and y. This is an isometry. It's distance preserving. Now, when I say, and this is a standard definition, that the map is a quasi-isometry, it means that the distance is preserved up to a multiplicative constant. That is, if this is equal to 2, if this is equal to 2, means that points which are some distance apart, their image is not 2 times this distance apart. So it's more flexible than an isometry. And from the other side also, if the points, if the images are some distance apart, then it means that it implies that the points themselves are some distance, some bounded distance apart. So this is the definition of this is the usual definition of a quasi-isometry, and I think I wrote it somewhere here. Yes, here. So if you have finite sigma 1 and sigma 2 such that this double inequality is satisfied, it implies that the map is continuous and injective. This is also called by Lipschitz. Yeah, sigma 1 and sigma 2 may vary, yes. If this is valid for some sigma 2, then if I take another sigma 2 which is greater than this one, it will be obviously...
Yes, so then what happens to this?
Okay, you are right. In fact, I come back here. And so here, we take sigma 1 and sigma 2 as the best constant satisfying this. That is, sigma 2 is the smallest constant satisfying this inequality, and sigma 1 is the biggest constant satisfying this inequality. And then the distortion of f, well, I could take sigma 2 over sigma 1, but I want to take log sigma 2 over sigma 1 so that if sigma 2 is equal to sigma 1, which means that the map is an isometry, then I want to say that the distortion is 0 and not 1. Okay? So this is the definition in this paper of the distortion.
So,
yes?
in omega subset of S2,
yes.
you are taking which metric? You are
always the spherical metric.
And in R2?
In R2, I'm taking the Euclidean metric.
So there you are getting same thing for both of them.
Where? I made a mistake? Where?
D of xy.
D is same for both you have written the note.
Yes, you are right. Yeah, in fact, I did. Yeah, it's a mistake, but it's not really a mistake. But when we put the you are right. We put the distance, and then you have to guess whether it is a distance in the range or in the domain. Yes, you are right. I use the same letter here for distances, and you have to understand that this is different. Yeah, thank you very much. Yeah, this is correct. Yes, I make this several times. In fact, it's usual to make this abuse of notation. Yes, you are right. Okay, and then Milnor defines, well, a Milnor minimal distortion map is a map whose distortion is minimal among all maps. I take all maps. So this is, the paper is called A Problem in Geography, and this is a geographical map. I want to build a map where this by Lipschitz distortion is is minimal. So he has some. He proves then. He proves then this theorem. So yes.
Yeah. So what does that minimal mean? I mean, it's a subset of R that set of a distortion.
Yes.
Yeah, that's a subset of R. Then I mean we have a definite order, right?
Among all the maps, I want a map of. I'm looking for a map among all possible geographical maps. I'm looking for a map a method of drawing a geographical map which minimizes this distortion.
Yeah, that's right. But I'm asking why not minimum? I mean, why do use the word minimal? Is there any particular reason for that? I mean,
well,
you can say about the
yes.
minimum, right? It's in R. I mean, they're all real numbers.
Yes. Yes. I mean, it's not. Is it obvious for you that a map of minimal distortion exists? Because I mean, if you take the map which contracts everything, or no. I mean, you want a map which is injective, at least, you know. And I don't think that there's no theorem which tells you that a minimal distortion map exists.
Okay.
And this is, I think, here it's. This is the theorem here for existence. I mean, you have to prove this.
Okay.
Yes. So for every set, if the cardinality is at least 3, then there exists a minimal distortion map. This needs a proof. In fact, I mean, if you read the proof, it's really a very complicated elementary topology. He has the map first on a countable set of points, and then he has to show that he can extend and so on. It's really topology. So this is existence. And then he asks the question, so there exists a geographical map, which is minimal distortion in the sense I proved, I explained. Now, the question is about the uniqueness. Is this map unique or not? The differentiability, is this map differentiable or not? The constructibility, is there a way of constructing this map? Because geographer, you want to explain to them how to construct this map. They don't know anything about mathematics. You have to give a method, constructibility. Constructibility of the map and of the minimal distortion. You have so any given omega. How do you find its minimal distortion? This minimal distortion, in fact, is associated to a subset of the sphere omega. Okay, so I'm more or less telling you what he is writing in his paper. He says this problem is unknown. The result is unknown in general, except in one case. The answer to this question is unknown, except in the case here I said is positive. In fact, it's not positive. The answer to all the I copied. I didn't copy correctly. The answer is unknown. The answer is positive. Is unknown except in this case. So the answer is positive in the case where omega is a spherical disk. So what is a spherical disk? It's just I take a point and then I take this is a spherical disk. Point the set of points where the distance to this point is less than a certain constant. This is also a spherical disk. This is also a spherical disk. So this is a spherical disk. In the case where the map concerns a spherical disk, then the answer is positive, and the distortion. So he gives a formula for the minimum distortion in terms of the diameter of the disk, or the radius alpha of the disk, spherical radius, and this is independent of the radius of the sphere. Okay, and then he explains what is this map. What is this? He explains what is this, the map which realizes there's a unique map which realizes this minimal distortion, and he explains, and the map is, it turns out that the map is, we talked about it yesterday. I didn't put the name, but the map is, let me, okay. So I wrote here, F carries each great circle passing to the center of the sphere into a straight line in the plane. So so the map is here. This is the plane. So these great circles here will be sent to straight lines. This point will be sent to a point. These great circles will be sent to straight lines in the plane. The angles are preserved. The angles are preserved. So angle here is equal to the angle here. And what does he say again? The circles here, the circles around this point, the spherical circles are sent to circles. And that's it, I think. That's it. And then he says, I didn't copy everything he says, but he says this map is exactly, it turns out to be exactly the azimuthal projection which I showed you yesterday, which geographers use since 3 or 4 centuries. Without being aware, in fact, that this is the best map. In fact, they had the intuition, but nobody has proved this. And this is not the only instance in the history, you know, of knowledge that the craftsmen, you know, they use something for 300 years, and then a mathematician comes. He says, well, this is the best, the best map or the best object or the best thing which could have been used for this. For this situation, so this is the azimuthal. So this is the center. This is the center of the sphere, and the circles are sent to themselves, and so on. The map is not, of course, the map does not preserve angles. So as I explained to you yesterday, these are the ellipses. The ellipses represent the quasi-conformal distortion of the map. They are not all circles, but this map is used often in geography. And then something which I wanted to tell you also at the end of his paper, and also in volume 1 of his collected works. You see the collected works of some famous mathematicians like Raghunathan, or give me a name of a famous Indian mathematician. Yeah, Ramanujan, for instance. You have collected works. They printed after he. For Raghunathan, he's still alive, thank God. But the interest of building a collected works of a person like Milner, who is still alive, is that after each of his paper he makes some remarks on what is the current situation of the problem. In fact, so he asks these problems 70 years ago, and the problems are still open. Nobody answered them, and he adds to these problems, in fact. Okay, so he thinks that there's a similar result for the case where omega is a disk in the spherical or hyperbolic space of any dimension. In fact, even in the hyperbolic space of dimension 2, the smallest hyperbolic space, it is not known whether there is a geographical map which realizes all the problems, all the properties, which has all the properties we stated. But he asks the result for any dimension. And the target space is the Euclidean space of any dimension also. This is now, you see, these questions here are about uniqueness, constructibility, and so on. Now it's a more special problem. Take a geodesically convex region in the two-sphere, meaning a region where, taking a geodesically convex region simplifies the problem. If you want to draw, to take the image of a continent like India, it's more difficult. Geodesically convex means that when you take 2 points, then the shortest line between them stays in the set. So this is not geodesically convex. This is not geodesically convex anyway. So this is just a special case where the question is relevant. Is there a unique embedding in the plane which minimizes distortion? And I think the same question for convex, geodesically convex regions of the hyperbolic two-plane. If you remember in my first lecture, I told you that there are some natural problems which arise. I gave you this example even from the Euclidean plane. So you take a triangle. I said you take a triangle, and here another triangle. What is the least distortion? Is there a least distortion map taking this triangle to this triangle? And this turns out to be a non-trivial problem. It's a difficult problem. In fact, I wrote at least 3 papers on this, even for Euclidean triangles. The problem of geographical maps is for maps from the sphere to the Euclidean plane. You want to find least distortion maps. Okay, and now there is this question here, which is related also to what we are working on in Teichmüller theory. Suppose you have a distortion minimizing map, then is the distortion constant the same everywhere? Is it necessarily the same everywhere? So yesterday we talked about quasi-conformal maps, and today I will continue a little bit about quasi-conformal maps. And the question is, the question was, I have, say, a surface, a closed surface, and then another surface here, which has a different shape, and suppose both of them are hyperbolic, the fact that they are hyperbolic is not very important. Two surfaces equipped with, say, a Riemannian metric, and then you want the surface a priori has no reason to be conformally equivalent. There is no reason that there is a angle-preserving mapping between the two surfaces, right? The question which Teichmüller asked is, what is a best conformal map, a best close to conformal map, or a best quasi-conformal map? This is what he is. This is quasi-conformal means best close to conformal. And in his theory, a best quasi-conformal map, the conformal distortion, you remember this conformal distortion with the ellipses, infinitesimal ellipses, which go to circles, and then the circles which go to ellipses, and then we define the quasi-conformal constant by the ratio of the great axis to the small axis at each point. Okay, so in this theory, the quasi-conformal constant it is a result that for a best quasi-conformal map, the quasi-conformal constant is constant at each on the map, is the same at each map. So here Milner is asking analogous question. I don't think he had in mind the quasi-conformal theory, but he is asking the same question. For a distortion minimizing map, is the minimum scale constant on the whole surface? Okay, and then number 4, is the maximum scale minimized along the boundary? So this is a question, I mean, it's motivated by potential theory, in fact. In potential theory, I mean, when you study heat propagation and things like that, you end up with something. You want to minimize some energy, and then the heat must be constant on the boundary. So anyway, so this is also a question. So this is a set of questions which is, I think, interesting. Okay, so now I want to. This ends my yesterday lecture. I think it doesn't matter, right? We are trying to understand a few things. Okay, thank you. I just need the light. Yes. Thank you. So let me just remind you of something. So we have, let's say, we have all these geometries. So this is spherical. This is Euclidean. And this is hyperbolic. And we said that this surface being Euclidean means that when you take a point here, then there is a disk around it, which is isometric to a disk in the Euclidean plane. There's a more precise definition, which I don't think I know, which I don't think I want to tell you. There's the same definition here. So every point has a disk neighborhood, which is a disk which is isometric to some disk in the Poincaré plane, in the hyperbolic plane. In fact, maybe I should say more. I should say more. In fact, I want to say give a more precise definition. Uh, 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 I don't know if you have had such. I know that some of you have, but how many students have had this kind of definition? Yes, I know here. In fact, okay. Let me mention something. I want to mention it because also it reminds me of geography. Yes. No. No, it's not. No, the sphere is not locally Euclidean. You see, if you take a point on the sphere, and if you draw a triangle, spherical triangle, then the sum of the angles we said is greater than two right angles, so it cannot be Euclidean. So we are on the sphere. We are on a huge sphere, which is the you said locally Euclidean? Yes, okay, very locally, infinitesimally. You are right, yes. Yes, you are right. Yes, she's right, in fact. She said, I understand now your question. In fact, locally means for very, very small triangles. The very small triangles look like Euclidean triangles. But here the limit will be 180. The limit of triangles of the angles when you shrink the triangles to a point. Yes, you are right. But when I say, maybe the confusion is due to me. When I say locally, in the sense I explained before, it means that just each point has a neighborhood which could be small or which could be large. In fact, has a neighborhood, has a disk around it, which is the sphere. In fact, this is evident here because we are talking about the sphere, and here a disk which is not necessarily a small disk, right? Even a large disk is Euclidean. Okay, because the metric we are putting on the torus is the metric which arises from this identification of something in the Euclidean plane. So I take a point here. I'm not obliged to take a small disk, an infinitesimal disk. I could take a big disk. It is Euclidean. Even this big disk here is a Euclidean disk, right? Okay, so what I wanted to say, maybe I should give this more precise definition. So hyperbolic, let's say in the case of hyperbolic structure on a surface. So, in fact, the terminology here is comes from geography. In fact, those who started this, there's a so the surface. Let's say this is my surface S. There's an atlas. On S. What is an atlas? It's a set of maps which cover the whole surface, right? There's an atlas like for an atlas of the world, like an atlas on S. That is an atlas. Well, a collection of di, phi, a collection of di, phi, where di for each I, di is a subset of my surface here. I say I want to take it I want to take it simply connected. I want to take a disk. And phi I, and this is the domain. This is the geographical map which sends this di into the hyperbolic plane. So this is if I make a picture for each point, I have let's say a small disk here, and a map which takes this this disk into the upper half plane. This is the image. Okay, and I want to say that here on this disk I see like a disk of the hyperbolic plane. So I want to glue them all together. Another point here has this disk neighborhood. Another point here has this. But there must be some compatibility, right? So the compatibility, it's just this thing which the compatibility must say that I want to put it in words on the intersections of the disks. The maps, the corresponding maps in the hyperbolic plane are, well, restrictions of isometries. Let's say isometries, because this disk, which I took on the surface, I can start by sending it to a bigger one or a bigger. But I want some compatibility. I want to measure distances. I want to be able to measure distances here, not only in this small disk, but distances between a point in this disk and in this disk, and a point. I want to measure distance from this point to this point, and there are. I set something on a disk around each point. Okay, so the intersections here, I want them to come from isometries. Of isometries, they should be distance preserving. These maps between different charts must be distance preserving.
So what is the information on phi I? What kind of map phi I?
Homeomorphism. The information on isometries is between the images, the intersections. Yes, it's only there. So I'm gluing some patches, you know, of the hyperbolic plane to make a surface. You can see it in this way. I am gluing these patches to make them this surface, but I must glue by isometries. I must glue them by isometries. Otherwise, I will not get a notion of distance on the resulting thing. These gluings must be distance preserving. Yes. No, everything is right you said, but it's phi I composed with phi j inverse. Yes, this should be isometry. Yes, so she said it better than me. Yes, the phi I are symmetries, but on the intersection, the phi I composed with phi j inverse, whenever it is defined, should be an isometry. I don't think you need it to be smooth. Yeah, in real, yes, but I don't know. I don't think the smoothness is. I mean, the important thing is that it's. I mean, when you say that the smoothness will come from the hyperbolic plane. Yeah, you will carry it on the surface, but I don't think you need to impose it at the beginning. Yes.
Will phi would turn to isometry?
Huh?
The phi would.
Yes, yes. The phi i's will turn to be isometries after we have put this hyperbolic surface, this hyperbolic metric on the surface. Then the phi i's become isometries. let me say something. Uh, Something else? Yes.
Small question. Sorry, I'm interrupting you. Yeah. So, I mean, why H2? I mean, can't you do something about? I mean, replace H2 by C. I mean,
Yes, yeah, we can. H2, he is right. So if I replace H2 by C, and I do the same thing. So what is the complex? C is a complex, one-dimensional manifold. In fact, two real dimensions, but one complex dimension. So a complex surface, or a surface equipped with a complex structure, is exactly what I said. But here, the phi I goes from di into C, and the change of coordinates, whenever they are defined here on these intersections, are holomorphic maps. Biholomorphic, yes. Yeah, holomorphic is biholomorphic, yes. Holomorphic is biholomorphic. Yes, this is a very good remark. So, and in fact, how do I define a surface, a topological surface? Well, topological surface. Yes, yes. The change of coordinates is a homeomorphic. How do I define a projective surface? The atlas goes in the projective plane, and the change of coordinates is a restriction of a projective map. Or then you have many dimensions. This thing you can do in several dimensions, right? The same kind of in dimension 2, things are more things are easy. I mean, more things are easier. In dimension 3, you enter into a world of difficulties, of conjectures, of people who worked during 70 years, 80 years, in fact, different people, one after the other, on the map, on the problem whether there are topological structures which are not on which you cannot put differentiable structures, and so on and so on. So, but on surfaces, it's more or less. I mean, the theory is enough clear so that you can work on problems here. So I wanted to say something. Yes, let me say something because I need this. Okay, let us write here. This is the notion of foliation. This we need, and I think it's in the program of today's lecture, foliation, I think. So okay, so let's start with foliation on the plane. So I have my plane here. I want to draw just a set of lines. So you fill the plane with horizontal lines. This is an example of a foliation. You could make it more. In fact, you could make it. You could make it like this, so on. This is also a foliation. So what is a foliation? In fact, what is finally what is a foliation? How do I define what is a foliation on a surface? So let me tell you how you define a foliation on a surface. So you remember when we defined a differentiable surface? In fact, I said when we defined a hyperbolic surface, we took an atlas, and then the change of coordinates from here to here has to preserve something. In fact, here it has to preserve the hyperbolic metric. So for a foliation, there is an atlas so this is a collection of I called it I don't like the okay I took the I. There's an atlas covering my surface, covering the surface. This is on my surface. This is the I. Taking this into how did we call this? We didn't give a name for the domain. It's better. Okay, taking this neighborhood of my point to a subset of the Euclidean plane, Euclidean or not, subset of the plane, and then here I have another. This is dj. This is phi j. Take it here to another subset. And now the important is the change of coordinates. So the change of coordinates, I wanted to preserve. So in the plane, you choose in the plane. This is R2. This is R, and this is R. Then I have naturally a set of lines in the plane, which comes from the fact that I have a product of R and R, right? Horizontal line. So I want this map here. Whenever there's a change of coordinates on each intersection, I wanted to preserve the horizontal lines of the plane. So what do I get on my surface? I get at each point of my surface, I get a well-defined notion of line, because okay, I have a point. I know that I have a neighborhood which sends this to an open set of the plane, and if I take another map, something will be preserved. That is the notion of horizontal line. Means that the horizontal line has a meaning here on my surface. So a surface is equipped with a foliation. A foliation is, in fact, let me use the name. It's something like a geometric structure. Geometric structure means something defined by an atlas with change of coordinates. Okay? So this kind of geometric structure here is called a foliation. So for instance, we talked about the torus yesterday and the day before. So let's take this torus. Does it have a foliation? Is there a foliation on this torus? Is there a natural foliation on this torus? Yes. So you see, so if I take these horizontal lines, then for every point, every point, I have an atlas which is like the identity map, you see, which takes me this, which takes this disk around the point. I don't want to say small disk, but it's a disk. And then if another one, if I have another disk here, then well, the set of horizontal lines are compatible with each other. So not only this, but the torus has infinitely many foliations. In fact, I can take any angle here. I can take any angle here. This is a well-defined foliation on the torus, right? So the torus has many foliations. It is an atlas, yes. I mean, the atlas, yeah, but the atlas, the change of coordinates must preserve some set of lines. And here I'm saying that this is a set of lines because this atlas, you know, goes into the Euclidean plane equipped with a foliation, and here is the Euclidean plane. I can see it here directly. Okay. So yes. This is, yeah, this is a good question, but you see these curves here. Yeah, I mean, you don't mean a closed curve when you say a curve. Yes, it is a curve shifting constantly. Yes, it's something. Yeah, it is a curve shifting constantly.
For the torus, literally true because the transition.
It is naturally true for the torus, yes, because I can see it. Now, okay, in fact, before the torus, so let's talk a little bit about foliations. So foliations of the torus. Before foliations of the torus, let's talk about foliations of the plane. The plane itself is a surface. So what kind of foliations I can draw in the plane? So this is a foliation. This is a okay, and so on. This is a foliation. And then I continue, right? Yeah, not everything, but there are a lot of foliations, in fact. On the torus.
So why not everything? I mean, this is a single chart atlas. Talking about the plane, single chart atlas.
Yeah, the plane. I mean, everything you can draw on this atlas. You're right. You're right. But now let's see. Let's see on the torus. If I start like this, can I continue with a foliation? Okay, let's do it another way. How will I draw this? It has been years I didn't. So you see, no, not all the straight lines. I want this to be a closed curve of my foliation, and I want this a closed curve, and then I want the lines of my foliation to spiral along this around this one, and here to spiral here also around this one. You see, this one will come here, and then it will continue like this. It will continue like this, and then I want to fill them with huh? No, because I want to fill. Everything is filled, so I want to fill them with. I want to fill the rest Yes. So there are foliations like this with spirals. I mean, this question of foliations of surfaces, I will say many things about this. You attain when you go, for instance, to dimension 3, you attain to very difficult problems. You know, I think there was a question for many years whether you see this foliation here. I can also make it differently. So I have my torus, and then I have this will be a closed leaf of my foliation, a circle, and then in the complement of this circle, I want something to spiral along this. Okay. Yes. I can define. Yeah, foliation is defined using charts. Yes.
Suppose this map preserve the horizontal line but not preserve the vertical line.
No. Yes.
Can I say foliation?
Yes. Yes. I'm talking only about the horizontal lines. Yes.
So, but this also depends on the set of lines, right?
Yes. Yes. It depends on my choice because I decided that the foliation will be defined using these horizontal lines. I don't talk about the vertical lines. Okay, I want to proceed a little bit. Just to say that there are difficult problems, in fact, in dimension 3 on foliations. Foliations in dimension 3. I think that there have been a Fields Medal on some construction of foliations by Novikov, in fact, in 1950s, 1960s. Yes, there are difficult problems. So, but for us, I mean, I want to do things which are simple on the surface. Let me say the simplest things possible. Yeah, okay. So no, first about the torus again. So this is again the torus with this identification. So there's something which you must believe. I mean, you must know. I mean, believe me, I tell you, because I'm not going to give you a proof. You can imagine that. So now I take only linear foliations, right? Lines parallel to each other. I'm not doing spirals or things like that, like I did before. Only linear foliations. And the question is, okay, you see, so I follow. When I have a foliation, then these lines are called leaves. I will use this. Yes.
It has to continue like other side.
Yes. So I take a leaf. I take a leaf like this. And then it has to continue here. Sorry. Right? And then I arrive here. And then I have to continue. And then here. And I have. So my question is, does it close? Do I reach a point where? Yes, depends on the slope. Yes, this is an important thing which I will use. So, for instance, if the slope is 0, then I come back to myself. This is a foliation of the torus, but all the leaves are closed leaves, right? If I take so if this is a square, then if I take 45 degrees like this, then it comes back. This foliation of 45 degrees. All the leaves are closed leaves, which are parallel to this one. Okay. So the result you need to know here is that if the slope So any constant slope set of lines will give me a foliation on the torus, right? Because I mean you have to. This needs a proof, but because when I arrive here, well, I can continue with the same slope. The slopes are compatible with each other. So each point with the definition there, each point will have a neighborhood where there's a well-defined foliation on the plane, and the change of coordinates will preserve this foliation, because I just took here the foliation of the plane, which is exactly had the same slope as this one, and this is compatible, right? Yes. So the foliation on the plane is just this one which you extend. Here it's simple in this case. It is this one, the one with the same slope. Okay? So the thing which you need to know is that if the slope is rational, well, all the leaves of the foliation let's say are closed leaves. Closed leaves means compact if and only if the slope is rational. This is a result which I'm not going to prove, and which needs a proof, complicated proof. People who are doing number theory, they know this. They know this very well.
Does foliation have to fill up the space?
I'm taking all these lines, so they fill up. I'm talking here about this foliation, which is the union of all these.
So your space is union of all the lines, all the foliation.
Yes, I have my torus here, and my foliation is filling the space. Yes, I'm taking all these leaves. I'm taking all these leaves parallel to each other, so they have a well-defined slope here. This is the slope. If this angle is rational, then all the leaves are closed leaves. If the angle is irrational, then no leaf is a closed leaf. And furthermore, in the case of irrational angle, every leaf is dense. Every leaf is dense. There are uncountably many leaves. Yes. There are uncountably many leaves. Yes. In both cases, there are uncountably many leaves. Each leaf is what? A space filling. Yeah, it fills the space. No. This is in the This is in the case of the dense leaf. Yes. If the leaf is closed, then it's not space. In the irrational case, yes. Well, I don't know what he means by space filling, but it fills the space. Yes, it's. So these are the foliations on the torus. No. It's not the only foliations on the torus. It's not. These are the. We are talking here only about linear foliations. The foliations with constant slope. This is for foliations with constant slope. Our goal now is to do similar things on surfaces of higher genus, right? This is what I want to do. So what do I want to say more about this, about the torus case? So on the torus, we know that there exists such foliations. Maybe I talk. There's an important notion here which I will explain for surfaces of a higher genus, and this is a question of transverse measure. So this transverse measure is an invariant measure on transversals. So what does this mean? Okay, we don't have a color chalk, but it's fine. So you see, you have a notion now. You understand what is manifold. Did I say a surface is a two-dimensional manifold? Yeah, okay. Let me say something just to finish this for 5 minutes, and then we'll take a break. A surface is a two-dimensional manifold. So this means that, I mean, by definition, a surface, and this means that I have I have an atlas with values in, well, let's say R2. In principle, this is exactly what tells me what is a two-dimensional manifold. But then I can talk here about differentiable two-dimensional manifold, and then I have an atlas with values in R2 with differentiable coordinate chains. So I get a differentiable manifold. I can have here a surface also is, say, a surface is, say, hyperbolic two-dimensional manifold. I have an atlas with value with hyperbolic. The coordinate change are hyperbolic as isometries. So this means that my R2, I have to replace it with by the hyperbolic plane, and so on. So you have different kinds of manifolds. The surface can be a complex manifold. Means that I have an atlas with values here. It will be in C with holomorphic coordinate change, and so on. So each manifold, when you say I have a manifold, you must be more precise. You must say what kind of manifold I have. Complex manifold, and so on. So now here I have a foliation. I have a foliation. So this gives me an example of a foliation two-dimensional manifold. This enters in the same big category. So now when I have these foliations, I'm talking just now about this foliation on the torus. in fact, when I have foliations on some manifold, then I can talk also about hyperbolic foliations. I can talk about complex foliations. I can talk about Euclidean, for everything. Now this concerns the, I wrote it here, the transverse structure of the foliation. The transverse structure of the foliation. Let me say it just in a couple of words. So I have a foliation. Here it's one-dimensional. It could be two-dimensional. It could be n-dimensional. The transverse structure of the foliation means I take a transverse. I take a transverse curve. Or if the foliation is n-dimensional, in an m-dimensional manifold, I take an m minus n transverse. Here it's only one dimension, and I take a transverse curve. So, and I can have various structures on this transverse curve or transverse segment. The thing which is important for us there is that I have a transverse measure. A transverse measure. So when I take this transverse segment, this means a measure in the sense of Lebesgue measure. You know, my transverse arc becomes a space on which I have a measure. On which I have. You don't know about measure. You know measure theory? Yes. Okay. Very good. So I have a measure here. So I can say, well, this set is of measure one, measure two. I can assign numbers. So this is a transverse arc. This is one-dimensional. So I'm talking about measures on the real line or on segments of the real line. So what is proper to this measure? What is proper to this measure, in fact, so that it is a transverse structure? It means that if I move my arc, if I move my arc, this one, I move my arc by letting each point of the arc stay on the same leaf, then the measure is preserved. All these transformations, these are called. Let's complicate. Just if I move the arc so you see, I have when I move the arc, letting each point on the same leaf, it means I have a natural homeomorphism between the first arc and the final arc. Okay? The natural homeomorphism is I take this point, I know that I have moved the arc so that each point stays on the same leaf, so I have a well-defined point on the resulting arc, because there's one leaf carrying this point to this point. So these maps are measure preserving. And this is called a transverse measure for my foliation. And these play a major role in what in this Thurston theory. I will give you more about this after the break. Now it's time for the break?
Yeah, we can take a short break.
Yeah, okay. In 6 minutes. Yes? Mathematical definition of foliation? I just gave it, in fact. The definition I gave is mathematical, I think. If you want me to write formulas, I'm not able to write formulas. But I tried to explain mathematically what is a foliation, yes. This? No need? Okay. And the other one? No need also the other one? Ah, I have. Okay, so now we talked about, okay, let's suppose that you understand what a foliation means, and especially a foliation on the torus, and then we know what is a measured foliation on the torus. A foliation where, so this is my foliation, and I have a transverse. On each transverse segment, I have a measure, a Lebesgue measure. My transverse segment is a measured space. And all these measures on the transverse segments are compatible because when I move the segments along, leaving each point along the same leaf, then this natural map from here to here is measure preserving. Now we want to make the same on any surface. Any surface meaning like this one, and so on. This one. Or on the sphere. Let's start with the sphere. Can I draw a foliation of the sphere? Yes. So your friend is telling me, okay, this is, but is this? And then what do I do here?
But sir, it is not measure preserving, right?
It's not a foliation first. There's no foliation on the sphere because I have here these 2 points. I have here these 2 points which are different from all the others because from all other points I have a leaf of the foliation which passes through that point, and here I have no. So in fact this is a theorem. There is no foliation of the sphere. So those of you who did some geometry, some surface geometry, you know that maybe you know if I put here, there is no vector field on the sphere with no zero. Any vector field on the sphere should have a zero. You know this? Or on the disk, right? I cannot draw a foliation of the disk. If I start continuing here this boundary component, then there's a point here. The thing about vector fields, I mean, people are more familiar with. Students are more familiar with the vector field. At each point you have a vector and so on. And then the vector field has to have a zero somewhere or a singular point somewhere, okay? Yeah, continuous vector field. Yes, she is right. When I say vector field, I say continuous vector field. Yes, there is no foliation continuous vector field. So if you know about vector fields, then you know about foliations, because a foliation is a vector field where you forget about the length and the orientation. You see, in vector field means at each point you have a vector, and then the vectors, the set of vectors gives you integral lines where the vectors are tangent to these integral lines, and then you forget about the orientation, and you get a foliation. So if I have a foliation of the disk, it has to have singular points. Singular points mean just points where the foliation is not a foliation. There's no foliation at all. Tell me, please, a little bit higher. This is, I was thinking about the closed disk. If you talk about if you talk about an open disk, then you must specify what you want the foliation to do on the boundary and so on. This is a closed disk. This is a closed disk. This is a closed disk. Yes. If I talk about open disk, it's a little bit more. I mean, you have to say more. You have to say more. Yes. You see, because yeah, okay. I mean, if your disk is an open disk, then you can throw out the singularities to the boundary. You don't see the boundary, right? Okay. So I'm talking about compact surfaces here. So okay. So now we want to study this kind of yes. So what do you do on the sphere, for instance? You study foliations of the sphere with singularities. And then what is a singularity? You draw a picture and you say this is the model of my. This is topological model for my singularity of the foliations I want to study on the sphere. And then after you have seen this, you can ask me, okay, in fact, I have here a foliation of the sphere with two singular points, right? This one and this one, right? Can I have a foliation on the sphere with three singular points? Is this possible? Yes, I tell you here, in fact, well. Here, but then I introduce other kinds of singularities. This is a singularity now. If I introduce this third singularity of this type, then I must introduce other kinds of singularities, and so on and so on.
For any meromorphic form, we can just create singularity.
Meromorphic forms have singularities, but I think you have to. They have to have an even number of sectors at each singularity. This one here, which is like this, does not come from a meromorphic form. But you are right. This is this is a good point. People who study meromorphic forms, they naturally study foliations. Yes, foliations. Okay, so the thing which I wanted to say here, the thing you see, there's something which you must learn. In fact, topology. Only surfaces with zero Euler characteristic. Have you heard about Euler characteristic? Okay. Have foliations with no singular point. This is not a difficult thing. This you learn, or also instead of this, I can say admit vector fields In fact, because you can, when you have a foliation or a vector field and so on, you can compute the Euler characteristic by taking sums of something, sums of index of the so this has some index, this singularity, this has another index, and so on. And if you have no foliations, then the Euler characteristic is 0. Okay, this is something which, I mean, if you don't know this, you just believe. You just believe this.
So,
yes.
In this diagram, the straight lines are the...
These are foliations with singularities. And to say what is this object singularities, you just draw a picture. And then these are leaves also. They can be dense or they can be whatever. And they are, because they start at a singular point, they are called singular leaves, but they are called also separatrices because here they are separating several regions. Is there any importance for singular leaves? Yes, the singular leaves play important roles. Yes, I will explain. Yes. Okay, so now I want to now in this Thurston theory you have we want to study foliations. I wrote it there, in fact, foliations on this kind of surfaces. On this kind of surfaces. So so we must admit singular points, and we must say what is the local model for each singular point. These are foliations with singularities. Of the following form. So I draw pictures, in fact, either like this or like this, or 5 separatrices, 1, 2, 3, 4, 5, and so on. So this is three separatrices, this is 4, this is 5, and so on. I admit only this kind of singularities. So, for instance, I will not admit this kind of singularity. This is not allowed. And then, from what I said somewhere, that you can compute Euler characteristic from the number of singularities, I know that there are only a finite number of them. Huh? Okay, because why? We have when you compute Euler characteristic of a foliation or a vector field or of a surface and so on, you add some numbers. And these numbers are all of the same sign. Same sign. No, there's a number associated to this. Say this is say -1. This is -2 because I have 4 parentheses. -3. I'm not saying that these are the exact numbers, but it's almost like this. You know, and when you add all these numbers, you find the Euler characteristic of the surface. So it cannot be infinite.
It's kind of different triangulars, singular.
Yes, because the relation with the Euler characteristic is that from this kind of singularities, you build a triangulation of your surface and so on. So this is an exercise. I mean, no, it's not an exercise. It's quite a result, but it's given as an exercise in Thurston's book, you know, I told you, I gave you three references. And these three references, if you study them, if the three of them, you become a great mathematician if you understand. So the first reference is this paper I said, minimal stretch mass between surfaces, which is on the internet. The second reference is these notes on hyperbolic, the geometry and topology of three manifolds. And the third reference is a book written by Thurston, which is called The Geometry of Three Manifolds, I think, The Geometry of Three Manifolds. The Geometry of Three Manifolds, I think. Otherwise, it's something like that. The Geometry of Three Manifolds, and it's called Volume 1, and it's the only volume. In fact, Volume 2 was never written. And this thing about Euler characteristic from index of foliation is given as an exercise, a half-page exercise. So if you read this book and if you try to do the exercises, most of the exercises I don't know how to do because I have to spend several days on each exercise, and unfortunately I cannot. But if you are willing, this is an exercise. Yes. Okay. So we have foliations with singularities of the following form. Of the following form, either this or this or this, and so on. 6. Okay. Now we want to construct at least one. We want to construct at least one, say, and then you will see how you can construct many. In fact, there is a way of constructing many foliations. Let's say. So okay. So we start with. We already saw that a surface you can take two pair of pants and then glue them together, and then you get a closed surface of any genus. I mean, you take 3, 4, 5, 6. Okay. Now the pair of pants I want to now this is no more geometric, it's only topological. I want to draw foliations and then glue the pair of pants together, and I get foliations on the resulting surface. So let's see. I will make pictures here. So this is like this. This is a foliation on a pair of pants, and then I take another one exactly the same. Why not? Exactly the same. It has the allowed type of singularities here and here, allowed type of singularities. And then I glue boundary on boundary.
So what type of singularity?
This is a singularity. It's of this type. It's of this type. 1, 2, 2 singularities. Okay? Yes? The sphere I have taken before, this one, yes? No. When I draw foliations, I don't talk about metric. But this is, we talk only about the spherical metric. But for the foliation, there's no metric. Yes, exact, yes. Okay, so now you glue this part to this part, and what is the problem? Is there a problem in defining a foliation on this surface of genus 2? I find a foliation on the surface of genus 2 with 4 singularities of this type. The identification, yes. But what would be the problem with the identification?
Like,
Somebody said something? What does this mean? Compatibility of what? Well, this is the leaves. You see, the leaves are trailing everywhere. The leaves are the leaves are everywhere, and each leaf, each point here will go with a point here, and there's no compatibility to worry about. This is when I draw this, it means I have leaves everywhere. The leaves fill the surface. Right? I join, for instance, I'm not obliged, but I join this to this. Maybe I can join this to this. Why not? I mean, this is all topological. I join this to this, and a leaf which starts here, arrives here, you know, and then it continues. This is glued to this, and then it continues here, and maybe this is glued to this, and so on and so on. It wanders in the surface.
so there might be, I mean, if we join, there might be more similar points. I mean,
No? Where? From where would they come? Here, when I glue, I'm joining something like that, coming from here, with something like that, all transverse to the boundary, and there is no singular point at all. The leaf will come here, and then it will continue on the next one.
suppose one of the singular foliation that
No. What do you mean? One of the singular foliation? No. One of the singular leaves? Yes.
Singular leaves, yeah.
Yes.
That would attach to a non-singular leaf, maybe.
Yes. Maybe it goes to a non-singular leaf, and then it wanders in the surface. Then
it has to come to another single.
no, I never said this. This is an interesting problem. I mean, you have to study what does it happen when if singular leaves, the singular leaves, do they wander what is the closure of a singular leaf and so on. So this is the dynamics people who study this. Usually on much less complicated surfaces, on the torus, on things like that. You know. Yes. Yes, I will talk about this after. Yes. Thank you. So what I want to say here, you see, I want to highlight an analogy, and this will be important for us. Was it last? Yeah, I think it was yesterday. We were talking about hyperbolic structures on pairs of pants, and I explained to you two ways of constructing hyperbolic structures on pairs of pants, either by gluing ideal triangles, or by taking right-angled octagons and no, it was hexagons, and gluing the faces pairwise, and then you have these. So this is my hexagon: 1, 2, 3, 4, 5, 6. And then there's one on the other side, and then gluing, since they are right angles, you get this. Then I said also that you could change the length of the right-angled hexagon. We already said that the 3 determine all the rest. So if you change the 3 that you glue, then it's completely determined, the hexagon, and so on. Okay, here I'm saying something almost similar, and this is important because in Thurston's theory, there's also an analogy between foliations and hyperbolic structures. So here I'm drawing my pair of pants differently. I'm drawing it planar, so that I can see the foliation. Now, in Thurston's theory, something very important, these foliations that appear, most of them, I mean, except in some special cases which are, I mean, which complicate the theory, but at the beginning, the basis, all the measured foliations, all the foliations that appear are measured, transverse measure. There's a transverse measure. You remember I talked about transverse measure there? It means that when I take a transverse arc, I know what is its measure, right? It means in particular that I have a measure on this interval, on this circle here. I have a Lebesgue measure, an additive function, which satisfies some very natural property. I have a Lebesgue measure, and then you see, when I specify a measure, I specify the length. When I specify the length of this, I specify some number here. I specify some number here, and some number here. Let's say A1, some number here which is A2, some number here which is A3. They must satisfy some triangle inequalities, you know, because this will be the transverse measure of this big one. And then there's a transverse measure of this one, and the transverse measure of this one. So I cannot just say, okay, I take here 1 as a transverse measure, and I take here 1 as a transverse measure of this one, and then I take 100 as a transverse measure of this one, because what? You see, because the measure must be, there's a preservation of a measure. The measure of this arc must be equal to the measure of this arc, right? And the measure of this arc must be equal to the measure of this arc, and the measure of this arc must be equal to the measure of this arc. So there are some equalities, but simple equalities like triangle. I mean, in fact, okay, if I say, okay, I want a measure foliation on this pair of pants, where the transverse measure of this is 5, this is 4, and this is 3. They satisfy triangle inequality. Then I can find the correct configuration, you know, of singularities, so that I can build this measure foliation. So So the idea I want to convey is that you have hyperbolic structures on pair of pants. You glue them, you obtain hyperbolic structures on the surfaces. You have measured foliations on pair of pants. You glue them, you obtain measured foliations on surfaces. There's a classification of hyperbolic structures on surfaces using a decomposition into pair of pants. There's a classification of measured foliation on surfaces using decomposition of the surface into pairs of pants. And there's this theorem of Thurston, which I will explain. I have put it into the program. So we more or less said, I didn't prove that we have this big space, which is called the Teichmüller space of this surface here. This called, let's call it SG. This is G equals 2, G equals 3, and so on. The G is the number of holes here, Teichmüller space of SG. This is a big space. You remember what we said about the dimension? Yes, this is, and in fact, homeomorphic to a ball of dimension 6G minus 6. And then there's also a space which is space of measured foliations on the surface. I want to say now something which is not completely right, but I don't want to go into complications now. The thing is that there's a boundary here. There's a boundary. Like you have like you have hyperbolic space, we said that there's a boundary circle, right? And hyperbolic space of any dimension, it has a boundary sphere. And here the Teichmüller space has a boundary, which is the space of measured foliations. The two spaces glue very well together. The thing which is not correct is that here I have to take projective measured foliations, but let's not complicate. It's more or less this thing, measured foliations. And this whole, the union of the two is called this is the Thurston compactification. The Thurston compactification of Teichmüller space. When you have something which is like an open ball and you glue to it a sphere of the right dimension, then you get a closed ball, and on its boundary you get this. The boundary is that sphere. So this is what I want to explain to you now next.